We're continuing our study of eigenvalues and eigenvectors. So this is the second class that we're talking about eigenvalues and eigenvectors. And in particular, we reviewed a bit about how to find eigenvalues, which is to find the roots of the characteristic polynomial. And when you find the eigenvalues for the matrices, then you can find the corresponding eigenvectors by finding the solutions to, or finding the basis of the null space of those matrices A minus lambda I, where lambda is the specified eigenvalues. So that's the general like basics behind eigenvalues and eigenvectors. And then once we've established that connection between eigenvalues and what those numbers are and what the eigenvectors are, then the question becomes, what do we do with that information? What do we do with eigenvalues and eigenvectors beyond just being able to compute them? Well, the idea was that eventually we talk about something along the lines of diagonalizability. So there are going to be matrices that are going to be considered or categorized as diagonalizable and others that aren't. So again, this goes back to the beginning where matrices at first were either square or non-square. And then we talked about matrices that were either invertible or non-invertible. Now we're going to be talking about matrices that are diagonalizable or not diagonalizable. And invertibility does not necessarily imply diagonalizability. So you can have invertible matrices that are not diagonalizable. And does anybody remember the condition for a matrix to be diagonalizable? What is required? What is necessary? What is necessary in order for a matrix to be diagonalizable? And first of all, what does that even mean? Diagonalizable. And does anybody recall? No. So diagonalizability is dependent upon whether the eigenvalues that you find, if basically if you're able to find enough eigenvectors that are a basis to the underlying space. So for example, if you're dealing with the 3x3 matrix, the underlying space to that matrix, the column space and the row space, is R3. So in your process of finding the eigenvectors of that matrix, if you find 3 eigenvectors, then you have a diagonalizable matrix. If you don't find 3, if you find 2, or if you find only 1, then you have a non-diagonalizable matrix. So there's a few things I want to clarify about diagonalizability that I think I mentioned. So yeah, so let me start sharing my new screen here. So I want to clarify something that I think I mentioned. Clarification. Multiplying two diagonal matrices is commutative. So I I believe I said something about like, remember we talked about AP equals PD? And I said, because this is a diagonal matrix, I can commute them. That only occurs if both matrices are diagonal. P is not necessarily diagonal, so you can't swap P and D. Okay. So the commutativity aspect. So if A, for example, if AB equals BD, equals BA, this occurs if A and B are diagonal. So it's not, I think I mentioned, like I said in the previous lecture, that because you have one diagonal matrix, you're able to commute them. That's not true. It's true if only if these two were diagonal. If they were diagonal both, then you can commute them. Diagonal matrices, you can commute the product. But if it's just one diagonal matrix, then you can't. So so that's one clarification, okay? That I just want to make clear. The second thing was this equation, AP equals PD. Um, I think I just briefly just mentioned why this is um, a, why this is an equation that we utilize, because eventually from here what we do is we find that A is equal to PD P inverse, right? Or you can find that D is P inverse AP, right? Those are the two different ways to express. If this is true, then these two equations are true. Um, but I want to just clarify why this is true, right? This is, again, coming from the fact that A VI equals lambda I VI. For I, 1, 2, all the way to n. So this is saying that I am taking every eigenvector that exists, and I'm assuming that this is diagonalizable. So I'm assuming that the assumption is there are n eigenvectors, or I should say A has n eigenvectors, and A is an n by n matrix. So an n by n matrix, so let me just write this better. The assumption is an n by n matrix A has n eigenvectors. Okay. And so what we do is we create this new matrix P. And what is P? P is a matrix whose columns are the eigenvectors. So all the columns of P are the eigenvectors of A. Okay. And the eigenvectors themselves, if you were to put them all into a group, a set of eigenvectors, they're all independent of one another. They're linearly independent. So if you have a matrix that's n by n, where the n columns are linearly independent, right? Then we know that P inverse exists because P is an n by n matrix with n linearly independent columns. Okay. Okay. So then A times P, what is this? This is A multiplied by V1, V2, dot, 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 Vn. But this is the same thing as saying A V1, A V2, and A Vn. Now, why is this true? Yet you have to go back to the idea of multiplying matrices with one another. And then all of these are what? Lambda V1, lambda V2, lambda Vn. Why are they lambda? Why does it become lambda? Because Vi are all eigenvectors. So when you multiply an eigenvector by a matrix A, then it's equivalent to multiplying that same eigenvector and multiplying it by a scalar lambda, or in this case, lambda 1, which is in accordance to V1, and then so on and so forth. And what I want to clarify is, why is it that this here equals PD? That's all I want to really emphasize on. Why? Why is this PD? Why isn't this DP instead? And again, what is D? D, we wrote D as the diagonal matrix that contains all of the eigenvalues. Right? So if I multiply D and P, would I get the same thing as P times D? So what would happen if I do this? And compare that with what would happen to this here. What would be the difference? Would there even be a difference? So if we look at it, if we put our attention to this, what would happen when you multiply this out? Now, what might help you a bit more with this, what can sometimes be a little misleading or confusing, is this V1, right? And you just have one V1 thing here, and you're assuming this is a column vector. So what if I do this instead? V11, V12, all the way to V1n. And then this is going to be V21. This is V22 all the way to V2n, right? So, pardon me, this should be the other way around. It should be 2-1. It should be n1. First, this is the nth row, first column, and then this is the other way. This is 1, 2, and this is n2. And I do this all the way to the nth column. So this is going to be V1n. This is V2n. This is Vnn. What would happen if I multiply the matrices? What would it look like? We would end up with lambda. Well, remember, let's take this slow. How do we multiply matrices? We do what? first row, first column. And when I do that, the top, this one will be what? This would be lambda 1 V1, right? V11. And then if I continue this idea, if I continue this, this becomes what? First row, second column. So what's going to happen? This will be lambda 1 V12. This would be lambda 1 V1n. So the first row of the product will be the same as the first row of this matrix, right? And having a lambda 1 attached to all of it. And then by symmetry, what would we get? We would get lambda 2 V21, and then lambda 2 V22, all the way to lambda 2 V2n. And then so on and so forth. This would be lambda n Vn1, lambda n Vn2, all the way to lambda n Vnn. This is what would happen on this side. Now, what would happen on this side? I'd have the same matrix, V11, V21, Vn1. This would be V12, V22, Vn2, Vn1, V2, 1n. 1n, 2n, all the way to Vnn. And I'm multiplying this by lambda 1, 0, 0, lambda 2, all the way to lambda n. So let me move this down here so you won't confuse the equal sign. Now, when I multiply this out here, what is this going to look like? First row, first column, right? When I do that, all these zeros here cancel out all of these entries in the first column, and all I'm left with is lambda 1 V11. And then if I continue this, right, this here, so this first row with the second column, all the zeros here are going to cancel out all of them except for V12. So this would be lambda 2 V12. And then so on and so forth, right? First row, last column. This would have all the zeros here cancel everything out except for the V1n. So this would be lambda n V1n. And then I would continue second row, first column. The second row only deals with the first entry of the second row. So this would be lambda 1 V21. This would be lambda 2 V22, so on and so forth. Lambda 2 V2n. You go all the way down. This becomes lambda 1 Vn1. Do you guys see what happens when I go down along each of these entries here? To get these entries here, what am I doing? I'm taking each row of the first matrix and multiplying with the first column of the second matrix. So what happens inherently is that all of these entries here get multiplied by lambda 1. Then all of these entries here get multiplied by lambda 2, and so on and so forth. Sorry, it should be lambda n. Does everybody see what I'm doing here? What I'm showing you is why is it that A times P, the matrix A with the set of column vectors being eigenvectors P, why that equals PD and not DP? Do you guys see that now? Look at the column here. This column here has different eigenvalues for each of these entries. But what I want here to be is I want this first column to have the same eigenvalue, lambda 1. And the second column having the same values, lambda 2, and the last column being lambda n. So that doesn't happen here because each of these columns have different eigenvalues. But what happens here? I can now treat this first column is really what? Lambda 1 multiplied by the column vector v1. And this is lambda 2, v2, all the way to lambda n, vn. And this is what? This is p times d. This up here was d times p. So rightfully so, a times p equals p times d. Is that clearer from last time? Do you see why the product a times p, which results into this, is written as p times d and not d times p? So I just wanted to make that clear. It's because of the very nature of matrix multiplication, the way you do it with the row and then the column, the row and then the column. So this is the appropriate way to express that. So once we have that, we have everything else. We have that p is invertible, so then we have a equals, again, a equals p times d p inverse, or d is equal to p inverse times a times p. So when you write it this way, what you're saying is you can make A into a diagonal matrix. When you write it this way, what you're saying is that, pardon me, A can be written as a product or decomposed as a product of three matrices where one of them is diagonal. So we're all saying the same thing, just in a different order of things. So the conditions, I should say not condition, I should say requirement. The requirement for diagonalizability. The reason why I put it in parentheses, the S, is because it really means this. The two things that I'm going to say really are the same. They're the two statements are the same. So one of them is that for a n by n matrix to be diagonalizable, there must exist n eigenvectors for A. If you don't get n eigenvectors for an n by n matrix, then it's not diagonalizable. And we saw that in the previous lecture. And so in the last lecture, we just briefly talked about this idea of geometric and multiplicity, geometric and algebraic multiplicity. So that's the second statement, which is really just a reformulation of the first statement. So that says that if the algebraic multiplicity equals the geometric multiplicity, for each eigenvalue of A, then A is diagonalizable. So we have this term here called geometric algebraic multiplicity. And we have the other term called geometric multiplicity. Okay, and so let me just define what that means. What is an algebraic multiplicity? So an algebraic multiplicity is the exponent associated with the factor of the eigenvalue in the characteristic polynomial of A. In other words, it's the number of times that the factor repeats in the factorization of the characteristic polynomial. It's the number of times. The number of times the eigenvalue or root of characteristic polynomial is repeated. And then that's the first one. The second one is what is the geometric multiplicity? And the geometric multiplicity is the number of basis vectors they're called the eigenvectors in the null space of A minus lambda I. In other words, it's the number of eigenvectors in the eigenspace, or I should say, of the basis of the eigenspace. Remember, eigenspace, the eigenspace is this statement here. The eigenspace is the null space of A minus lambda I. In other words, the geometric multiplicity is considered to be the dimension of the eigenspace. Because the dimension is the number of basis elements. So it's just reformulating the same thing that we're expressing. We're expressing that the geometric multiplicity is the number of basis vectors in the null space, which is equivalent to saying the number of eigenvectors in the basis of the eigenspace, which is equivalent to just saying the dimension of the eigenspace. So the geometric multiplicity is the dimension of the eigenspace, and the algebraic multiplicity is the number of times that the factor associated with the eigenvalue is repeated in the factorization of the polynomial. So why do we care about this? Well, we care about these two things in particular because if the algebraic multiplicities and the geometric multiplicities all are equal, then it's essentially what you're saying is that there's gonna exist n eigenvectors. There will exist n eigenvectors for the matrix A. The moment that one of those algebraic multiplicities does not equal the geometric multiplicity of for a given eigenvalue, then immediately you don't have a diagonalizable matrix. So that's the significance, going back to Mir's question last lecture. That's the reason why, or was significance for the repeatedness of a root. So we can have a root of a characteristic polynomial repeat more than once. The question now becomes, if it's repeated more than once, which is the algebraic multiplicity, will it equal its geometric multiplicity? Meaning that given that eigenvalue, will we have enough eigenvectors to come out of it? It has to equal the algebraic multiplicity in order for that matrix to have a diagonalizable form. If it doesn't equal, then that means that you don't have enough eigenvectors that will come out of this matrix, which would mean that it's not diagonalizable. So you can't express it. You cannot express it as a matrix P times A times P inverse, and so on. Am I making sense when I say this? Any questions about this? Okay. If there are no questions, let me see. Okay, so for this matrix, so we have a matrix A. I want you, or what we're going to do together is find, so the first thing is find the algebraic multiplicity for each eigenvalue of A, and then find the geometric multiplicity for each eigenvalue and then determine whether A is diagonalizable. If so, express A as P times D times P inverse. Okay? So that's our task. The algebraic and geometric. So how do we do part A? What's the first thing we should do? How do we find the algebraic multiplicity for each eigenvalue? Anybody out there? Find the eigenvalues. Yes. So I need to find the eigenvalues to even speak about algebraic multiplicity. So how do you find an eigenvalue? How do you find the eigenvalues of a matrix? Of a given matrix? Multiply by eigendiagonal and then find the roots. Multiply by the eigendiagonal. Is that how you find eigenvalues? Where do the eigenvalues come from? What polynomial again? Remember, their eigenvalues are the roots of a specific polynomial. What polynomial are we speaking of in relation to eigenvalues? I've mentioned it a couple times in the above. A minus lambda I. You're close. We need more than just A minus lambda I. Not only, definitely going to use A minus lambda I, but what about A minus lambda I? It doesn't equal 0. It's that the determinant equals 0. This, guys, again, this is important. This is the characteristic polynomial. Characteristic polynomial of A. We call this the characteristic polynomial. Why? Because when we perform the determinant upon this matrix A minus lambda I get a polynomial. So don't forget that. So now what is that going to look like? A minus lambda I is going to be what? -1 minus lambda 4 2 -2 -3 4 minus lambda 0 -3 1 3 minus lambda, and this entire thing is equal to 0. Okay, so I'm taking the determinant of this matrix, which is A minus lambda I. Again, lambda is a scalar. I is the identity matrix, which is a 3 by 3 matrix. So I times the lambda will just be lambda, lambda, lambda along the diagonals, and I'm subtracting that with the matrix A. So that's why only these entries here are the ones being subtracted by lambda. Everything else is staying the same. Now what we have here is a determinant to compute. How do you compute this determinant? And the other example is much simpler, right? Cofactor expansion, very good. Now we can choose any row, any column, but there's one row or one column that is more convenient. It's more convenient to use than the others. Right, the far right column, right? So we're going to do cofactor expansion along third column. Okay, so if I do that, then this here will equal A31 C31 plus A32 C32 plus A33 C33. The nice thing is that A32 is 0. So if this is 0, this entire thing here can be just disregarded. It vanishes. So A31 is -2. C31 plus A33 is 3 minus lambda C33. But what is C31 and what is C33? This is -1 to the 3 plus 1. This is -1 to the 3 plus 3. This is the minor 3, 1. This is the minor 3, 3. And the minor is just the determinant of the submatrix that crosses out that row and that column. So in this case, we're crossing out So if I take this guy here, -2, right? -2, I'm gonna cross out the wait, 3, 1. Pardon me. The numbers here are again just rearranged. This is fine. 3, 3 is fine. This should be 2, 3. Second row, third column, 2, 3. And this should be first row, third column, first row, third column. So this should be just swapped. Okay, and so that means I'm getting rid of the first column, first row, third column, and I'm looking at this submatrix. This submatrix is going to be my determinant. So it's going to be -3, 4 minus lambda, -3, 1, plus 3 minus lambda, and C 3, 3. I'm getting rid of the third row, third column, and this becomes -1 minus lambda, 4, -3, 4 minus lambda. And so then now I have two 2x2 matrices to compute the determinant of. And when I do that, I get -2. This is -3. This becomes +3 times 4 minus lambda, plus 3 minus lambda. And then cross multiply like in this fashion again. So this becomes -1 minus lambda, 4 minus lambda, minus -12, which is +12. And all of this is equal to 0. And do you see how we have a polynomial now with just lambdas in it? So from here, what I'm going to do is I'm going to see if things come out nicely somehow. So if you look at this here, I can factor out a 3. If I do that, this becomes -6. This is -1 plus 4 minus lambda. So this here becomes -6, 3 minus lambda. And this is nice. This is really nice. So whenever you have a lot of these terms here, don't expand everything so quickly. Be a little more patient, because what you notice sometimes is ways to factor. Factoring helps, because now look at this. I can factor this 3 minus lambda from each term here, and I'm left with 3 minus lambda. This is -6 plus, and this whole thing here, right? -1 minus lambda multiplied by 4 minus lambda plus 12. The reason why I'm doing this is because if I were to expand everything out and write it as a polynomial in standard form, you would still try to solve the polynomial, which the best option, the most optimal option would be to be able to factor. And factoring, well, in this case, might be it's going to be a cubic polynomial. Factoring cubic polynomials aren't always so clear and straightforward. That's the end of my... Yeah, you're going to have to get another one. Well, at least a few more sheets, I would say, maybe. Well, congrats, you reached the end of your textbook. Yeah, we've written a lot, haven't we? It's a lot of stuff. So, so yeah, I'm just saying this as a piece of advice. Solving polynomials in general isn't an easy task, particularly when the polynomials are of degree 3 or higher, and if you're not able to factor it, so then right away. So then one technique was what we mentioned before all this talk about eigenvalues. We talked about rational roots theorem, right? And synthetic division. So that's another way you can use, another technique you can use to find a way to factor polynomials if need be. But then if you can't factor, if there's no factorization, then it becomes and a more of a calculator question, which it becomes more complicated. So in general, finding the roots of polynomials isn't an easy thing algebraically when the degree gets a little bit higher than 3 and so on. So factoring is always a way to simplify things. So that's why I didn't expand everything immediately. I saw that, hey, look, I can do 3 minus lambda. I can take that out. So that's already, I already have my eigenvalue. Lambda is 3. I already have one. Now I have another few terms here that I can combine and simplify. So this becomes -6. This is -4 plus lambda minus 4 lambda plus lambda squared plus 12 equals 0. So this is 3 minus lambda squared minus 3 lambda, and this is plus 2. Okay, that's nice, because now I can factor that out. I can take lambda minus 2 lambda minus 1. So then what are my eigenvalues? Lambda equals, well, this is really nice. 1, 2, and 3. One, 2, and 3. And what are the algebraic multiplicities for each one? That should be pretty straightforward as well. These all only appear once. So the algebraic multiplicity for each lambda, or for each eigenvalue, equals 1. This is the best, I should say, this is the most like ideal scenario, that you have a 3 by 3 matrix and you have 3 distinct eigenvalues. So this is an example where a 3 by 3 matrix has 3 distinct eigenvalues. The moment, yeah, it ended up being really nice, really clean, right? 1, 2, 3. The moment you have distinct eigenvalues and you have n of them for an n by n matrix. So if you have a 10 by 10 matrix and you have 10 distinct eigenvalues, immediately you have diagonalizability. Why do you have that immediately? Well, because they're distinct, that means if they're all different, that means that they all repeat only once. So your characteristic polynomial is factored into n, or in this case 3 distinct factors, and it only repeat once. So immediately finding the eigenvalues or the eigenvectors are going to be 1 from each. Each eigenspace will only have 1 eigenvector. So you're going to have 3 distinct eigenvalues with three eigenvectors that come from those eigenvalues. And so immediately you have a diagonalizable matrix. So if you have distinct eigenvalues, you immediately have diagonalizability. But diagonalizability is not, how should I say this? So this is a scenario where it's a sufficient condition. Diagonalizability has a sufficient condition, which is if you have distinct eigenvalues, then you have diagonalizability. But it's not a necessary condition. You don't need distinct eigenvalues to be diagonalizable. As we've seen in other examples last lecture, we had a 3 by 3 matrix where you only have 2 eigenvalues that were distinct, but one of them repeated. And that had a diagonalizable form. And we also saw another example of a matrix that also had the same scenario. It had two distinct eigenvalues, but it didn't have the same number of, it didn't have enough eigenvectors to produce that can be found out of that matrix. So it wasn't diagonalizable. So diagonalizability is not dependent so much on the eigenvalues themselves. It's dependent upon the fact if you have enough eigenvectors to go around, which is connected to the algebraic multiplicity equaling the geometric multiplicity. If they don't equal, then it's not diagonalizable. If each algebraic multiplicity for each eigenvalue equals its geometric multiplicity, then yes, it's a diagonalizable matrix. So I hope that is driven home and that's clear. So from here, what is the geometric multiplicities? So again, to find the geometric multiplicities, we kind of already know what the story is going to look like at the end. But for the completion of this problem here, this example, the geometric multiplicities is related to the number of eigenvectors that exist for each eigenspace. So what's the first eigenspace? So let's look at the eigenspace of lambda equaling 1. What is the eigenspace of an eigenvalue? The eigenspace of a vector of a matrix A. So how do we find that eigenspace? Anybody? How do you find the eigenspace? Does anybody know what I mean by eigenspace? If you guys don't know, then let's go back to what I mentioned here. The eigenspace of a matrix is the null space of this matrix A minus lambda I. So when I'm finding the eigenspace for A, given lambda equaling 1, then what am I really finding? I'm finding the what? The RREF. Well, I'm going to use the RREF, but before we talk about what computational procedure we're going to perform, what is it that we're finding again? The general idea is A minus lambda identity. Yes, but again, it's the null space. I hope so. It's the null space. It's the null space of A minus I, because lambda is 1. So it's A minus lambda I, but lambda here is equal to 1. So it's just A minus I. To find the null space of A minus I have to find the row reduced echelon form of A minus I. So that's where the row reduced echelon form comes into play. So then what is that? So what is A minus I? Well, A was what it was. And then when we subtract 1, we get -2. 4, -2. You get -3, 3, 0. And you get -3, 1, And then you subtract it by 1, you get 2. Right? So I think that's, let me just make sure I have written up here good. Yeah. Okay, so now this is the matrix A minus lambda I. A minus I. A minus I. And I want to find a null space of this. So then that is why I must find the row reduced echelon form of this, because that information from the row reduced echelon form I can use to find what the null space looks like. So we can use our calculators for this. The row reduced echelon form of this. So I'm going to use my calculator here. Okay, so then do second matrix, 3 by 3, edit. And you get -2, 4, -2, -3, 3, 0, -3, 1, and 2. Then we do row reduce echelon form. I want to find the row reduced echelon form of that matrix A. And I get 1, 0, -1, 0, 1, -1, 0, 0, 0, which is what's expected, right? We're expecting there to be only one free variable because we're expecting only one vector to be in the basis of this eigenspace. So we're expecting this to be the case. So then from here, what can we say? X1, right? X1, X2, X3. So then X1 is equal to X3. X2 is equal to X3. And X3 is equal to T or some other variable. So then what is, so I just want to make sure this is clear. What is the solution, or what is the null space? The null space of A minus I, which is the eigenspace, okay? What is this? It's a set of all vectors, right? That look like this. What is the solution? T, 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 or in other words, T, 1, 1, 1. It's a set of all vectors that are what? Scalar multiples of 1, 1, 1. So then what's the eigenvector? It's 1, 1, 1. So if I call this lambda 1, then I'm gonna call this V1. And so then what can we say? What's the geometric multiplicity of lambda 1? What is the geometric multiplicity? The geometric multiplicity of lambda equaling 1 is what? Is 1. Why is it 1? Because the dimension of the null space of A minus I is 1. Why is it 1? Because there's only one eigenvector. It's only one basis. Is that clear, guys? So that's our first eigenvector. Okay, let's get the next one. So to get the next one, I need to look at the eigenspace of A for lambda equaling 2. And what is that? Null space of A minus 2I. That's right. Now we're talking. It's the null space of A minus 2I. So I need to find what A minus 2I looks like. So A minus 2I, what is that going to look like? A minus 2. So this becomes negative 3. This becomes 2. This becomes 1. And everything else stays intact. Okay, and then I put this in my calculator. I just rearrange certain things. So this is negative 3. I'm only going to rearrange the diagonals because that's the only thing that changes. 2 and then 1. So I go to the home screen and I just repeat the command up here. I'm going to get, let's do math as a fraction. So then the row reduced echelon form of A minus 2I is 1, 0, negative 2/3, 0, 1, negative 1, and 0, 0, 0. So this is going to be x1, x2, x3. So then what do we get? What information do we get from the row reduced echelon form? X1 minus 2/3 x3, right? It equals, right? Why does it equal? Because this is really the equation that we get from the first row, but then we get the x1 equals 2/3 x3. X2 minus x3 equals 0, which means that x2 equals x3, and then x3 is nowhere to be found in the row reduced echelon form because it's free. So we call this the free variable. Now, what is the null space of A minus 2I? Well, it's the set of all vectors that's a scalar multiple of what? Scalar multiple of 2/3, 1, 1. Because any scalar multiple is in the null space, right? I can create another vector. If I make this equal to 3, then when I multiply this out, I get what? I get 2, 3, 3. This vector is also inside the null space of A minus 2I, which means this is also another eigenvector. An eigenvector is not unique. What's unique is it's the direction in which the eigenvector is going, but the uniqueness, which one of those scalar multiples I choose is not unique for eigenvector. But I'm going to treat this one as the one that I want because it's whole numbers. Every entry here is a whole number. So this is an eigenvector. of lambda equaling 2. So again, what's the geometric multiplicity? The geometric multiplicity of lambda equaling 2 is 1. Because I only have one eigenvector. And the geometric multiplicity equals the algebraic multiplicity, which are both 1s. So far, so good. We have an eigenvector, we have another eigenvector. Then the last one. What is the eigenspace of lambda equaling 3? Well, it's the null space of A minus 3i. So what is A minus 3i? A minus 3, you get -4, you get 1, and you get 0. And everything else stays the same. Okay, I'm gonna do the same thing one last time of finding the row reduced echelon form by editing the 3x3 matrix I have here and just changing the diagonal matrix entries. This is 1. This is 0. And then I use this row reduced echelon form and I get this. And I can convert that to a nice fraction. So then the row reduced echelon form is 1, 0, -1/4, 0, 1, -3/4, 0, 0, 0. So then from here, again, I got the x1, x2, x3 going on here. So then from this information, I get that x1 is equal to 1/4 x3. X3 is equal to 3/4, sorry, x2. X2 is equal to 3/4 x3. And then x3 equals x3, or I can just write it as t. So this equals 3/4 t, and this equals 1/4 t. What does this information tell me? It tells me that a vector in the null space of A minus 3i looks like t. So the vector here looks like t, 1/4, 3/4, and 1. But I don't want these fractions. I like having whole numbers. And I can do so because I have this fraction that I can multiply by a certain number that gets clears the denominators from each entry. So what should I multiply this vector by so I can get a vector with integral entries? 4, right, Baldwin? That's a good idea. So this becomes 1, 3, 4. So this is the eigenvector. For lambda equaling 3. So V3 is equal to 1, 3, 4. I found 3 eigenvectors, and they're all linearly independent. They create the base. They themselves, when you put them together, are a basis for all of R3 because you have 3 linearly independent vectors in a 3-dimensional space. So it's R3. So it's a basis. So then immediately what we have here is the geometric multiplicity of lambda equaling 1. Oh, sorry, 3 is 1. So this is the case where in this example each geometric and algebraic multiplicities equal one another for each eigenvalue. And so then the conclusion is, hence, A is diagonalizable. And so then how do we write A now? A can be written as P times D, P inverse. What is P though? What is the matrix P? Our three eigenvectors. That's right. And P is also not unique because the eigenvectors aren't unique in terms of which ones I select. And the order of the columns, the reason why it's not unique is because you can rearrange the order of the columns based upon what eigenvectors you want first, last, or in the middle. So it's just natural, right? It's just natural to be very nice and say the first column goes to V1, which is associated to angle to lambda 1. And then V2 is the eigenvector that's associated with lambda 2. And then V3 is the eigenvector associated with lambda 3, with lambda equaling 3. I can do that, but I can also rearrange it. Do you guys understand? So it doesn't have to be the first one, the second one, third one. I can rearrange that. But just for consistency, the first one was what? 1, 1, 1, right? It was 1, 1, 1, then 2, 3, 3, and then 1, 3, 4. So 1, 1, 1, 2, 3, 3, and 3, 1, 3, 4. I hope you guys can better appreciate matrices now. I think that's like out of all of this, right? Out of all the things that we've discussed over the past 22 lectures, I know a lot of this stuff after years go by, you probably will forget because that's just, if you don't use it, you're gonna forget. But I hope the lasting effect of taking this class is you understand how much more significant these numbers are in the matrix. It goes, and there's much more to speak about, of course. But now when you look at a matrix like this, there's so much to say. Like talk about linear independence, talk about eigenvalues, eigenvectors. Oh, of course. That's the reason why we were even doing this again. But of course, now our attention to detail is to the geometric and algebraic multiplicities. But your homework assignment, your web work, which is up right now, is exactly a bulk of it is exactly on this topic. Eigenvalues and eigenvectors, in particular, diagonalizability of matrices. So you're gonna have a slew of these problems. Yeah, yeah. But eventually, when you do enough of this practice, it's also very systematic. You get the eigenvalues. That's number one. So whenever you have this like large, grand task or objective, right? You always want to break it down to sub goals and tasks. So to determine whether a matrix is diagonalizable, which is the grandiose task, is first, let's find the eigenvalues. Find the eigenvalues, well, you have to find a characteristic polynomial. The characteristic polynomial depends upon finding the determinant of a minus lambda I. Boom, you got that. You factor or try to solve the characteristic polynomial, you get the eigenvalues. Now, once you have the eigenvalues, you find the eigenvectors for each respective eigenvalue, which goes back to finding the null space of that A minus lambda I matrix. Now you have to go back to null space using the row reduced echelon form business and being able to interpret row reduced echelon form for homogeneous systems. And then once you're able to do that, you're able now to determine the eigenspace, how big is it in terms of the dimension, depending upon how many eigenvectors you get from that eigenspace. If that geometric multiplicity, which is the number of eigenvectors in that eigenspace, is equal to the algebraic multiplicity of that eigenvalue for each eigenvalue, then it's diagonalizable. And essentially, that just means that you have enough eigenvectors that come from the eigenvalues. So if you have 3 eigenvalues, such as the one we see here, distinct ones, and we have an eigenvector for each, then we have 3 eigenvectors, and now we can create a matrix P where each column vector is the eigenvector corresponding to the eigenvalues. So this will be my P now. And so the idea is now I can find P inverse. And good thing is I have a calculator for that. So I got 1, 2, 1, 1, 3, 3, 1, 3, 4. So I want to find the inverse, take the inverse, and boom, I get 3, -5, 3, -1, 3, -2, 0, -1, 1. So I got my P inverse. And then what is D going to be? So D is kind of dependent upon what P is. Because P1, because this is the eigenvector V1, this is V2, and this is V3. This eigenvector is associated with lambda equaling 1. This is lambda equaling 2, and this comes from lambda equaling 3. So because these here appear where they are, then that diagonal matrix will be 1, 0, 0, 0, 2, 0, and 0, 0, 3. So I can represent A, which was what? -1, 4, -2, -3, 4, 0, -3, 1, 3. This, which represented A, can be rewritten as P. And what is P? 1, 1, 1, 2, 3, 3, 1, 3, 4. This is P. D is 1, 0, 0, 0, 2, 0, 0, 0, 3. And P inverse is 3, -5, 3, -1, 3, -2, 0, -1, 1. And so we can verify whether this is true. and it will be. But let's just computationally verify this. So then let me use the D diagonal matrix for D. And so here I'm going to have 3. Let me just see, does this go all the way to P? No, it doesn't. Okay. So if I write this as A multiplied by D, which is the diagonal matrix I just plugged in, times A inverse, which is P inverse for us, I should get exactly the original matrix, right? -1, 4. And that's what I did. Okay, so this is a way of, in a sense, decomposing a matrix A as a product of these matrices. But if you want to view it from the version of diagonalizing matrix, so this is, let me just go back. So this version here, A time equals P times D times P inverse, this is like a decomposition. So this is the perspective here is decomposing the perspective. This is decomposing A. Or you can think of it as factorization, right? But for matrices, they like using the word decomposition instead. But really, it's like saying factorization. But matrix world, we treat it as decomposition. So I broke up A as a product of 3 matrices, where one of them is a diagonal, the other 2 are invertible matrices, and they're inverses of one another. That's that perspective. But when I write it this way, when I write it this way, I'm writing it in terms of the perspective here is diagonalizing A. These are 2 different things related to the same central concept, which is diagonalizability. Both of them talk about diagonalizability, right? But they're 2 different viewpoints. One of them is decomposing any matrix, if it's diagonalizable, into a product where the middle matrix is diagonal. The other perspective is you take a matrix A, you multiply it by matrices so that you diagonalize that. The result is a diagonal matrix. Do you guys see that? So here I'm decomposing A as a product. So this is like my end goal, right? That's the perspective I'm looking at, diagonalizability. I'm taking A and I'm multiplying and I'm writing it as a product of 3 matrices. In this perspective, I'm taking A and I'm multiplying by these 2 matrices so that I get a diagonal matrix. So this is my goal here. My goal in that diagonalizing a matrix A is getting a diagonal matrix. My goal here in decomposing A is getting a product of matrices. Do you see the difference? This is the goal behind this perspective, and this is the goal behind this perspective. We're speaking about the same thing, diagonalizability of a matrix, but one of them is the decomposition of a matrix, and the other one is the diagonalization of a matrix. Is that clear? Do you see the distinction? So one is the actual diagonalization procedure, and the other one is the decomposition using a diagonal matrix of a matrix. I hope that makes sense. So in this perspective here, we're actually saying, hey, if I were to multiply A, which is -1, 4, -2, -3, 4, 0, -3, 1, 3. If I take this matrix and I multiply on one side by P, which is 1, 2, 1, 1, 3, 3, 1, 3, 4, and I multiply it by this matrix, 3, negative 5, 3, negative 1, 3, negative 2, 0, negative 1, 1. Then I get the diagonal matrix 1, 2, 3, which it's not just diagonal, it contains the diagonal entries are the eigenvalues. Is that understood? So if I take the matrix A, this A is not the same as the one we have, right? This is P for us. I take that and I multiply it by the answer, which is our original A, and I multiply it by the matrix A again. What I should get, the result should be the diagonal matrix 1, 2, 3, which is true. Okay. Any questions, guys? Any comments about diagonalizability? It's a pretty sophisticated topic. And the thing is that there's more than one way of decomposing matrices. This is one way. There's something called the LU decomposition of a matrix. There's some which LU stands for lower and upper triangular matrices. So there's another way to decompose matrices as a product of two matrices where one of them is a lower triangular and the other one is an upper triangular. That's one way to decompose another matrix. Another way is called the QR factorization or the QR decomposition. Q stands for orthogonal matrices. So that's where we're gonna head into. Hopefully we have some, yeah, after this lecture we have like three more lectures left. Yeah, we'll see how much we can get into the factorization decomposition of matrices. But there's several other kinds of decompositions. This is just one of them. This is the first one that we will touch upon. Okay, so any questions about this, guys? The procedure is always going to be the same kind of idea. Eigenvalues, from the eigenvalues, eigenvectors, from the eigenvectors, you see whether or not your matrix is diagonalizable. The factorization perspective or the decomposition. Yeah. All I'm saying about this is that this idea of diagonalizability can be viewed in two different regards. You can view diagonalizability as a way to decompose a matrix into a product of three matrices, where the middle one is the diagonal matrix, whose entries are the eigenvalues. So you can view diagonalizability from the perspective of, let's take a matrix, and if it is diagonalizable, let's do so. Let's use that fact of being diagonalizable so that we can re-express the matrix as a product of three matrices, where the middle one is a diagonal matrix and whose entries are eigenvalues. So that's one perspective, one way of looking at diagonalizability. A matrix is diagonalizable if you can write it as a product of three matrices, where the middle one is a diagonal matrix. That's one way. Another way to represent or to talk about diagonalizability of a matrix is saying, hey, if I have a matrix A, then can I find two matrices where that when I multiply it together, I get a diagonal matrix? It sounds like I'm saying two completely different things, but it's really the same. The idea of diagonalizability is the same if I view it this way or if I view it this way. It's just from a different take. It's a different take on it. This way here, I'm viewing it from the perspective of let's decompose or factor the matrix A. From this perspective here is let's do something to A, which is to multiply two matrices by A, one on the right and one on the left. Let's do that so that when I do so, I get a diagonal matrix. So one perspective is let's diagonalize A, which is this one here. Let's make A into a diagonal matrix by multiplying by these two matrices, which is what we need to find, what those are. From this perspective, we're saying, hey, I have a matrix A, let's decompose it so that the middle matrix here is a diagonal matrix. All of these here appear, they're the same, they appear, they're the same, they're just in a different order. One is a diagonalization procedure, the other one is a decomposition procedure. They're related, but it's just two different viewpoints. I don't know if that makes sense. Okay. Now, I want to talk about two more things, and then we will be done with this aspect of diagonalizability of matrices. The eigenspaces that appear are all subspaces, right? They're all subspaces. So this is a subspace right here. This is a subspace of R3. This is a subspace of R3. And this is a subspace of R3. These subspaces, if you were to find the intersection of these subspaces, the intersection of each subspace is 0, the 0 vector. So something that's in here can never be in here and can never be in here. It can't be in there because they're completely like not in the span. So eigenspaces, in a way, you can think of it as it decomposes the space that's underlying the underlying vector space. That's another way of maybe not the word decompose, because then we just talked about decomposing a matrix. You can maybe use the word splits. It splits the space into subspaces that, when you put them all together, give you the underlying space. But if you find the intersection of those spaces, the only thing that's related to them is 0. That's important because we will hopefully we'll see with the QR decomposition of matrices, this idea of I guess you can say decomposing or breaking down an underlying space into subspaces. This idea of breaking down a vector space into subspaces where each subspace has nothing in common with the other space other than the 0 vector is a very important concept. So the very nature, the very procedure of finding the eigenspaces, finding the null spaces of each of these A minus lambda I stuff, if you find the null space for all of those matrices and you union those subspaces together, you get R3 altogether. So I'll touch upon that. And another thing I want to talk about is that, yeah, and this gets more interesting. I just want to touch upon it. I'm not going to go into heavy detail. But the matrix A satisfies its own characteristic polynomial. That's a very, very profound statement We're not going to get into the nitty gritty of it because that is a bit more advanced. But if you give me any characteristic polynomial of a matrix, that matrix itself satisfies its own characteristic polynomial. What does that mean? So let me see if I can go back to 20, right? Let's see the eigenvalues. I want to go back to a simpler, yeah, there we go. So I'm going to go back to this example here. So I'm going to copy this example and put it here. And then the characteristic polynomial was this, right? Whoops. Okay, so we've been so concerned with finding the eigenvalues of a matrix based upon its characteristic polynomial that we just keep it as a factored form. So let's actually write the characteristic polynomial of A as a polynomial in standard form. So this is 3 minus lambda, right? Multiplied by -1 minus lambda, right? And so then when you multiply this out, you get what? -3 minus 3 lambda plus lambda squared. So the characteristic polynomial is lambda squared minus 2 lambda minus 3. Now, I'm not sure. I would venture to say that very few of you have dealt with polynomials in this manner that I'm going to show you. I'm pretty sure most of you have dealt with polynomials as a function, as a real valued function, which what I'm saying is the input is a real number and the output is also another real number. That's what this polynomial is really saying, right? I have an input and this input is a real number. And when I plug it in here, I get another real number, right? But think about this. Polynomials are functions. And for the longest time, you probably dealt with functions. Like I just said, the input is a real number, but the input doesn't always have to be a real number. The input of a function could be a matrix. So what would this look like if I plugged in the matrix A? Now this A is not a variable for a real number. It's a variable for a matrix. So what is this going to look like? So the input is a real number. The input here is a matrix. So it's a squared minus 3, right? That makes sense. So this would be a squared minus 2 times a minus 3. Agreed? Does everybody agree with this? Paul was like, yes, everyone agrees with it. Because I said it. Okay. If that's true, then what happens when I get A? Right? A is a what? A is 2 by 2, right? A is a 2 by 2 matrix. So if I take a 2 by 2 matrix and I square a 2 by 2 matrix, I get a 2 by 2 matrix. If I take a 2 by 2 matrix and I multiply by a scalar, I still get a 2 by 2 matrix, and a 2 by 2 matrix minus 2 by 2 matrix is good. But what happens when you subtract by 3? Does that make sense? If I get a 2 by 2 matrix and I subtract it just by 3, does that at all make sense? Ah, great idea. Hey, what if I put an I? because I is really what I is one in the world of um in the world of matrices, right? So you can think of this as a to the zeroth power. But of course, it's not one, it's I. It's not one in the sense of the word one in the way we deal with it as a real number. It's one in the sense of the world in the word of in the world of matrices, which is I. So it should be I. Now, what happens when I compute this? What's going to happen? Well, what was A? A is 3, 0, 8, -1. So when I square this, what would I get? Get 9. I get 0. I get 16. And I get 1, right? 24 minus 8 is 16. So I get 9, 16, 0, 1. Minus 2 times 0 times A becomes what? 6, 16, right? -2, 0. Minus 3, 3, 0, 0. What happens when I subtract these two here? Or let's just put this all together. I get 9 minus 6 minus 3, and I get 0. I get 16 minus 16 minus 0, and I get 1 minus, which is plus 2 minus 3. Guess what I get? I get 0. I just showed you that the characteristic polynomial of A can be satisfied, quote unquote, satisfied with itself. And this is true for every polynomial, characteristic polynomial. No matter what matrix you get, if you find me the characteristic polynomial of that matrix itself is a solution, quote unquote, to the characteristic polynomial because it equals 0. Of course, this 0 is the matrix 0, the 0 matrix. That's pretty interesting connection that it goes beyond just finding the characteristic polynomial. That's why it's called characteristic. It's specific to a matrix A. It characterizes what A is. And that is a unique polynomial. It's unique. So given any matrix A, you can find its characteristic polynomial. And that polynomial, when you plug in A, gives you 0 every time. And this is a theorem called the Cayley-Hamilton theorem. And of course, at that level of discussing this theorem, there's the idea of proving it to be true, and that requires a bit more advanced machinery and mathematics. But I just wanted you guys to understand that the characteristic polynomial, there's more to it. And associated with the characteristic polynomial is the minimal polynomial and other regards. But I wanted to show you this because sometimes we have a limited exposure to things such as polynomials. So we're thinking polynomials are just x squared and we're only plugging in numbers, but no, we can actually plug in matrices. And that's pretty eye-opening because when we talk about polynomials, this idea of polynomials is actually very profound. The way they teach it, right, is very like the most significant aspect of polynomials is you can graph it and it crosses the x-axis, and then you move on, and then you can maybe factor it, which is cool. You can find the roots, and that's it. But the world of polynomials is it's actually much more complex. It's much more significant than just finding the x values, finding the x-intercepts, plotting it, and just moving on with your life. So you can actually utilize polynomials for more than just plugging in real numbers. It's actually something you can plug in other things as well. Plug in. So this idea of plugging in, right, goes beyond just plugging in real numbers. You can plug in matrices. And I remember when I first understood this, I was like, I didn't know you could actually do that. I thought for a long period of time, I thought that you can only plug in to functions numbers. So that was to me, it was very revealing about what more you can do with algebra in general. So I'll leave you guys with that for today. Okay. Okay, so we'll move on from here.